Hey everyone, may the force be with you. Right, today we are going to be talking about forces and not the midichlorian Star Wars forces. We are going to be talking about physics, right? The force that you talk about in physics. And so let's dive right into that. The learning objectives for this, or the things you'll be able to do when we're done with this, is be able to define force and show how you calculate it. You can explain how forces affect the motion of matter. Remember, matter is just pretty much everything in this universe except like energy and things like that, light and heat. You can determine the net force of an object, distinguish between balanced and unbalanced forces, and be able to differentiate between mass and the weight of an object, right? A lot of times people think they're the same thing, but we will kind of see that, or we'll see today that they are not really the same thing. So, what is a force, right? Again, not the kind that you saw Yoda exhibiting in the previous slide, but force is something that we deal with every day, right? Whether you know it or not, it is just something that is a part of everyday life. The cool thing about physics is we get to give it numbers, right? We get to quantify it, dive down into the very smallest details of what happens in daily life, right? So, a force is just a push or a pull that causes an object to move, stop, or change direction, right? And again, every day you do that. Objects that you manipulate do that. Uh, these are things that you see happening, constantly. But in physics, a force is anything that makes an object accelerate, right? So basically, changing the velocity of something. When we think of accelerate, we think mostly of it just like speeding up. But remember, it's just a change in that velocity, so it can actually like slow down, right? So if an object is stationary, it won't start moving without a force. Remember, we talked about inertia. An object at rest tends to stay at rest. So if you have this huge boulder sitting out in a field, it is just going to sit there until some force acts upon it. And so forces come in pairs, right? And they have a magnitude. Remember, we talked about scalars and vectors in a previous lesson. So something that is a scalar just has a magnitude. It just has like a measurement, right? So if you're going in a certain direction, you could say, I just walked like 2 kilometers. That is giving something magnitude. You're putting a size or some quantity to it, right? You're giving it a number. And a direction, when you have a force, you got to give it that magnitude, but you also have to give it a direction, right? You have to know which way that force is pushing or pulling. So that is a vector. Y'all remember, a vector gives you both magnitude and direction. A scalar, just a magnitude. So force is a vector quantity, what I just mentioned. And so here you see, right, it's giving you both of those things that a vector gives you, which is magnitude. So in this case, 5 newtons. And it's also giving you a direction. In this case, it is north or up, right? And you see that arrow right there pointing upward. That is giving you the direction. And then again, the magnitude is this 5n. And so this is a vector, magnitude and direction. Magnitude is the 5 newtons. Remember that capital N stands for newtons, and we'll get into exactly what a newton is in a second, but that's how you measure force, right? And direction is just that north or upward direction. You see the arrow accounting for that. All right, so if we want to calculate measurements, we have to give the force some kind of a unit, right? The way we use the metric system for things like length, right? Meters, centimeters, millimeters. Without those, it would be very difficult to calculate lengths of certain objects, right? Same thing with force. It'd be difficult to calculate different amounts of force if we didn't give force some kind of a measurement. And we talked about that earlier, right? That capital N, it stands for Newton. An SI unit for force is a Newton. And so whenever you see that capital N, that's what we're going to be talking about is Newtons. All right, so a Newton is a force that causes 1 kilogram mass to accelerate at a rate of 1 meter per second squared. So you don't need to pay a whole lot of attention to that, but that's how they define a Newton, right? And so 1 Newton, like I mentioned earlier, it's just equal to 1 kilogram of mass times meter per second squared, right? And so the important thing to remember, though, is just when you see this N right here, that is what we are doing. We are calculating force. And remember this formula, y'all. We saw this already in a previous lesson, but force equals mass times acceleration, right? That's just what it's saying, right? The force is mass times acceleration. The mass of something, you put mass in kilograms, grams, milligrams, and the acceleration is just how quickly it's changing its speed, right? And so that is force equals mass times acceleration. So for force measurement, we use a spring scale to measure force. So we're going to take a little bit of time right now to go ahead and do that. So work, it says in pairs, you can do that or individually, and observe how the mass and newtons correspond to this on the spring scale. Measure and record the mass and the force it exerts downward for three objects. So take this time to ask your teacher for the spring scale and go ahead and work on this section. All right, so now let's talk about combining forces. When you're talking about an object, you want to also include net force. Sorry, when you're talking about forces and objects, you definitely want to talk about net force, right? That is the overall force acting on an object after all forces are combined. So if you think about your car, like say you're driving and you run out of gas and you're by yourself, you're in a parking lot, right? So you're kind of close to the gas station and you have to push the car by yourself, right? So you get, put the car in neutral and just kind of try your best to push it while you're standing like in the driver's side. Anyways, when you're pushing it, that there's a certain amount of newtons that you're exerting on that car, a certain amount of forces. But if you see like two or three people, hey, you need some help, and they come and they get behind your car and they push it, and your car is going to move a lot faster because you have more newtons of force behind that car, right? But what you do is you add all of the forces that those people are contributing to the push. Right? So forces in the same direction, you add them up because you are all going in the same direction. So you're adding to that force, which again is going to speed up the that car. Forces in opposite directions, you actually end up subtracting them because if you think about it, if you're trying to push the car in one direction and someone is like on the other side trying to push it in the opposite direction, some of that force is canceling out the other force, right? And to get a better understanding of that, let me just kind of show you this simulation right here. Well, let's see this right here, right? You have 10 newtons of force in this case. Let's say it's going in the right direction or east, and then you add another 10 newtons. Altogether, that 10 newtons plus 10 newtons equals 20 newtons, right? But forces in the opposite directions, you subtract them. So you have 10 newtons going right or east, and then on the other side, you have 7 newtons going west. Then 10 and 7, the bigger number is what you put there, so it's positive, so it cancels out and you get 3 newtons, right? So some of that force again in opposite directions cancel each other out, so you're going to subtract that. And so let's kind of see an example of that with this simulation right here. So you have the simulation, and let's go ahead and put this right here, this. And so this is just kind of like a little simulation that you'll see. This person right here accounts for 50 newtons of force, right? And these are the sums. So this is when it's all added up. You see right here, if you put all these guys right here on the left, it is going to add those forces, right? So you had this guy was worth 50 newtons. This one was worth 50 newtons, so it's 100. This one looks a little bit bigger, so it's probably going to be worth a little bit more. Yeah, so this guy by himself was just worth 100 newtons. So altogether, you have 50, 50, 100. So altogether, that is 200, right? The sum of the forces. And let's just throw this big guy in there too and see what happens. And so, yeah, and you can tell right here. So we went from 200 to 350. So this guy was worth 150 forces right here, right? That's what he's pulling. And so if you were to hit go on this, the forces right here cause the sum of the forces cause the blue team to win, right? But if we return this here and you have these forces right here, and remember we talked about that earlier, that they cancel each other out, right? So you see right here, you have 50 newtons on one side, 50 newtons on the other. And so the sum of the forces are zero because they are canceling each other out, right? So we'll throw this big guy here. Now you see there are a lot more forces here acting on this side. So there are 150 newtons going into the left direction, right? But if you add this guy right here, it's going to cancel that out. And then if you hit go, there really is no change, right? Because the forces have canceled each other out. And that's what we saw right here, right? The tug of war. Think of these as the guys, the blue team, all on one side. They had a net force, and they just straight up, went to the left. These guys right here, they and let's do that right here, right? Let's copy. Let's put one guy. Um, Let me throw one more guy right here. There's still, they tried. There was still some resistance on this side, but the blue team won because the sum of the forces, they favored the going to the left, and there were 100 more newtons of force going to the left. And so this is a similar example right here. When forces are applied in the same direction, they are added to determine the size of the net force, right? So they're both trying to push this piano. This person is 25 newtons of force, pushing it in the right direction. This person, 20 newtons in the right direction. So altogether, right, the 25 plus 20 gives you those 45 newtons to the right in the same direction. Right, but in a different direction. Here again, these guys are playing tug of war, a lot like we saw with the red and blue team. When two forces act in opposite directions, you subtract the smaller force from the larger force to determine the net force, right? Because you see this dog is larger right here, probably exerting more force on the rope. And so because it is exerting more newtons, right? Two more because it's 10 and then 12 over here. You see that it's got two more newtons of force. So chances are this bigger dog is going to win that tug of war, right? The net force will be in the same direction as the larger force. So the larger force was 12. So you see right here, 12 in the right direction. So you see this arrow right here is going in the right direction, right? So in the same direction as the larger force. All right, so we kind of saw this already in that like tug of war example that we saw before. Balanced and unbalanced forces, right? Forces occur in pairs. We talked about that earlier, and they can be either balanced or unbalanced. All right, so let's talk about balanced forces, right? These are the forces in each direction when they are equal. So if there's more than one force present, it doesn't necessarily mean that it has to cause an object to accelerate, right? And if another force balances out the first one, there will be no acceleration at all, right? Think of both guys weigh the same, pulling on a rope in opposite directions with an equal amount of force. How much will they move, right? And we saw that earlier right here with the this simulation, right? We return it here, and you put people the same amount of force on both sides, and you hit go. This would be called balanced, right? It's balanced because you have 50 newtons on the left side, 50 newtons on the right side, and they are exerting the same amount of force. So these guys are not going anywhere. It is balanced. And so balanced forces do not cause a change in motion. They are equal in size and opposite in direction. And the net force is zero, right? Which is what we saw in that simulation, 50 going to the left, 50 going to the right. They cancel each other out. So the net is zero for that. And there you go. And you can see too, a lot of times are represented with an equal length of an arrow right here. So the red arrow and the blue arrow are the same length, which means it's the same amount of force on both sides, which should mean a net force of zero. All right, same thing with these guys right here. Arrow on the left, the red one is the same size as the one on the right, which means that they are exerting the same amount of force, which means they have balanced forces and they're at a stalemate, right? It's not going one way or the other. So here you see forces may cancel each other out and produce no net force. So this is something you all may see if you are sports fans, right? If these football players push on each other equally as hard, will either one move? And if they are the same strength and the same size, have the same mass, then they'll probably cancel each other out, right? And it'll be a stalemate. So another example right here, the ground pushes up and gravity pulls you down, right? So if you're sitting in a chair right now, it's a good thing that you have that chair there, because if someone just came and pulled it out from under you, you would fall to the ground, right? Because gravity is pushing you down, but the chair is pushing you up, right? So in that case, it is a balanced force. Gravity pulls down on you, the ground pushes back up, or the chair, whichever example you're using, and this is what keeps you where you are, which is a good thing, right? So in this case, gravity is a good thing. If it all went away, we would just float up into the atmosphere, and who knows where we would stop, right? So you are right now living an example of a balanced force. So more balanced forces may cancel each other out and produce no movement, right? That means there is no acceleration when it is at zero, when the movement is at zero. So here's another example, right? I always like these comic strips of Far Side, but here you see there is a certain amount of force that this kid is trying to exert on the door, but unfortunately for him, it's a pull, right? If he would have exerted a pull force, he would have opened that door, but he is exerting less force than he needs to bust that door open, right? So yeah, it's just kind of a funny example of this unbalanced forces, but that door is not going anywhere because he is not exerting the forces to either push it through the bricks or, use his common sense and pull on the handle. Another example, we saw the simulation earlier, right? These guys are at a stalemate if they're both have exerting the same amount of force on both sides of the rope. All right, so now we're talking about unbalanced forces. So if the multiple forces acting at one time are not balanced out, they're not equal, then acceleration can and will occur on the object, right? If one side of the scale has more mass, then gravity will accelerate it down. And so that is an unbalanced force, right? So if you see something moving, then chances are there is an unbalanced force at work. Think about that boulder I talked about before. If it's just sitting there, its acceleration is at zero because it's just sitting there. It's not changing speed, right? It's just there, and it is balanced. Gravity is holding it down. The ground is holding it up, and it will not move unless someone comes and just pushes that boulder down a hill or something, right? Then there is some movement, there is some motion, and there is an unbalanced force. Kicking the ball causes it to move quickly in a different direction. So again, if a soccer ball is just sitting out on the grass, it's just going to sit there, right? Unless a force acts upon it, in this case, someone coming and kicking it. But even if the wind blows, right? Sometimes if the wind blows hard enough, it can move that soccer ball, right? It is an unbalanced force because the wind is causing it to move. So an unbalanced force always causes a change in motion. The net force is greater than zero. It has to be, right? Because if it's zero, that means it's just standing still because the forces that are pushing it are doing it at the same with the same amount of newtons. But if you get something greater than zero, then that means that there is some motion in the object. When unbalanced forces act in opposite directions, you can find that net force, right? So right here, again, let's go back to these guys right here. See 50-50, so this is a balanced force, right? But if you throw this extra guy right here, now you see the sum of the forces, you have more newtons going to the left, and so these guys are going to win this little tug of war right here, right? And that is because they are unbalanced forces. 100 newtons going to the left force and only 50 going to the right. Right. So this would be an example of an unbalanced force right here. And overall, it's going 50 newtons to the left. Right. So an unbalanced force in opposite directions, you can find the net force, a magnitude. Remember, that's just giving something numbers, right? Some kind of quantity to it. The difference between the two forces. So in the other one, we saw, what was it, a 50 newtons guy. One guy was 50 newtons worth of force. The other one was 50 newtons worth of force on the blue on the left side. And the one on the right was only 50, right? So 100 newtons going up against 50 newtons of force. And then in the direction, the left guys, the ones on the blue, they went to the left, right? Because there was a larger magnitude going to the left. And so that was the unbalanced forces, sorry, cause it to move in that leftward direction. If you're talking about the simulation that we just saw with the red and the blue guys. Right, so unbalanced forces here you see the representation. This red arrow is shorter than shorter in length than this blue one, which is just showing you that this guy right here, this guy's a beast right here. He exerted 6 newtons of force on this guy right here, which was only 3 newtons, and so overall, this guy right here had exerted more force, right? 3 more than the one on than this guy over here. So these guys two playing tug of war, right? So which guy right here would have won the tug of war? If you guessed this guy right here, he's exerting more force pulling on this piece of rope right? So overall, the force is going to go this way to the right. And you see that representation here, the red arrow going to the left is a lot shorter than the one that goes off to the right. Right, so just kind of showing these unbalanced forces are going to help this little green guy win this tug of war contest. And here you go, 4 newtons on the left side, 10 newtons on the right. Overall, 6 newtons going to the right. So unbalanced forces causing acceleration. Here you have a random object. Right? And you have 5 newtons of force and 5 newtons of force pushing on this object right here. Multiple forces can combine to move an object that has too much inertia for one force alone, right? The forces add up together. And so that makes sense for those of you who have, tried lifting or pushing something that is way too heavy just for yourself. So what do? You ask someone to help you, right? What you just saw was like 2 people pushing on the same box, right? That was kind of like those 2 arrows pushing on that random object. That is just an example of it. Notice that all the new forces are pointed in the same direction and they add together. So instead of only 5 newtons of force pushing the object, now there are 10 newtons of force pushing. Again, you're just adding up those objects if they're going in the same direction. All by himself, one person might not be able to push a car, but with extra friends pushing it, it becomes much easier, right? Because the forces are added up together. And so unbalanced force, right? This, you can have this happening too, where you have this object, right? And then the last example, we saw that the box was the object right here. And you have 5 newtons of force going in the right direction, 5 newtons. So altogether 10 going right. And you have these 5 going left, right? So in which way will the object end up going, right? If you're following the what we've been talking about. If forces are not equal and are acting in opposite directions, a negative acceleration can and will occur. Can or will occur. The forces will subtract from each other. Right, and so notice that the forces are unequal and pointed in the opposite direction. So they are unbalanced and work against each other, or one partially cancels the other out. Right, but if you see right here, just by doing this 5 newtons right here cancels this 5 newtons right here. So basically this is all we have is these 5 newtons right here. So the object will go to the right. The end result is that the forces on the left are slowed down by the one single one on the right. And so it's going to push it in that rightward direction. So here is just a review, right, of these balanced forces. You have 10 newtons right here going in this rightward direction, 10 newtons going in this left one. This is balanced, right? There is no acceleration or change in motion. Net force is going to be 0 because they cancel each other out. They are both kind of pushing them in towards each other. This one down here, you see a pull, right? So this was a push. You can see they're pushing on that object. Here they're pulling on the object in different directions. But because there's 10 newtons going this way and 10 newtons going that way, that is a balanced pull. There is no acceleration or change. The net force is going to be 0, right? So that is balanced. Unbalanced forces, you see right here, you have 10 newtons pushing to the right, 10 newtons pushing to the right. There's nothing pushing against it, so this will be unbalanced, and it will go off into this right direction, and it will have faster acceleration. So the net force right here is greater than 0, right? Again, 0 means it's standing still, but if something is being pushed, if it's unbalanced, you are going to have a number greater than 0 for the force. Same thing here, right? You have some pushing 10 newtons on this side, and just 10 newtons on this side. But because you have more on this side pushing to the right, they're going to cancel each other out, right? So unbalanced because they're going in opposite directions. It's going to be a little bit slower because, there is some resistance against it, but the net force right here is going to be greater than 0. All right, so now let's talk about the difference between weight and mass. So a lot of people think of these as like interchangeable, that they mean the same thing. And a lot of times we kind of do mean them to be the same thing, but technically weight and mass are different, right? Weight is a force of gravity acting on an object, right? So weight will be different whether you are here or whether you're on the moon. It will be different, right? Because there's different amounts of gravity here versus the moon. So the product of it is a product of the mass and acceleration due to gravity, right? So remember, weight takes gravity into account, and the unit is in newtons, right? So the weight for formula is equal to mass times acceleration, and it's due to gravity, right? So they do not mean the same thing. And so astronauts on Earth, the mass would be 88 kilograms, and their weight would be 863 newtons, right? And if you see that, the mass is the same whether it's on Earth or the moon. The mass, again, is 88 kilograms, but the weight of the astronaut would be 141 newtons, right? So a big difference, because if you're looking at, if you're talking about being on the Earth, there is gravity. On the moon, there is some gravity, but not nearly as much, right? And you can tell the difference in the weight, 863 newtons versus 141 newtons. So what did we learn? We learned how to define force and show how it's calculated. Remember, force is equal to mass times acceleration. It's basically just pushing and pulling on something, right? That's how it affects the motion of matter. Determine the net force of an object, right? So you just add up all those forces, and whichever ones in whatever direction you have more of, that's which way that object is going to go. Distinguish between balance and unbalanced. Remember, balance just means that you have the same amount of force on both sides canceling each other out, and so there's no movement. But unbalanced means that one side has more force than the other, and so there will be movement in the object. It's a motion. And then mass and weight. Remember, mass is going to be the same whether you're here on Earth or in the moon. It's the weight that is going to be different because of gravity.